Coming back to the Gerard presentation and fourth generation of district heating companies, probably the digitalization would be one of the most convenient way to reach this target of fourth generation. And as Energy Advice is Lithuanian-based company, and we developed EA-SAS cloud platform for the digitalization issues. I would share today knowledge and experience of Energy Advice through the digitalization in general, and what the value we created for the district heating companies also. So who we are a technology-based company. We focused on energy-intensive industries, and we develop and produce software, EA-SAS as a cloud solution, and EAPSM software as a desktop software for the electric grid analysis, and EAPSM hydraulic for the energy. Hydraulic system analysis, like compressed, incompressed fluids, thermal hydraulic calculations. So our cloud solution we divide in focus as from a marketing perspective to the boilers, biomass or CHP, for the heating, for the cooling applications, and ventilation also as building management. Coming back to the platform as general, our goal is to analyze, and because our part of business is providing services, consultancy services, we understand for such kind of services we need data. And a very useful application, cloud application, is when we have a lot of data on one place, and we can analyze this data and deliver a very deep analysis for our clients. So in general, we integrate all metering device, starting from the heat meters, electricity, water, gas meters. In fact, we don't have limitation on protocols or any device type, because we platform independent supplier. And of course, as usual, you can visualize data in the map on the real time. Coming back to the data, it's very important SCADA control systems and microcontrollers, because probably 80% of the data in the district heating side or industrial company side is on the SCADA control systems. When the SCADA supply data set points to microcontrollers, and microcontrollers collects and operate a lot of data, like a temperature, pressure, flow, and etc. So we collect data from the microcontrollers through Modbus, H1S7, Profinet, or whatever protocols, use OPC servers, and send data to the cloud through REST IP protocol. So we put our data, it's Energy Advice created software, data collection software, which is installed at the client side and in the virtual machines, and collect data from the meters, SCADA and SQL database, and deliver through REST IP to the cloud solution. As a platform, usually people require some data visualization, because usually people are users of the data, and this visualization becomes important to be flexible, that a program is not required to configure dashboards, and dashboards should be configurable by data analyst, process analyst, and all data visualize it in the dashboards. So we support multiple tabs, where you can create your tabs according to the process. Any language support, you see picture in Lithuanian language. However, our language could be Dashboards are dependent by user groups, so separate users in the company could use different dashboards, and all data in the dashboards updated in real time. But finally, a cloud solution, in our opinion, is not only data visualization and data collection. In fact, this data should create a value. So I mean, a value should do some mathematics, and this mathematics should somehow optimize what you have in operation and in future decision making. So we have inside technology, Airflow technology, it's Apache technology, where we run Python task inside each minute, each 5 minutes, each hour, each week, each month. And these Python codes are run on real data, what are collected from the smart meters, from the SCADA systems, and etc. So we can create Python as a provider, as a consultancy service, and you can do your Python as an analyst by yourself, or you can order this specific mathematics from the energy advice. And all these calculations are scheduled. If very complicated calculation exists and you're required to do a lot of calculation, it could be parallelized, cascade dependent calculations. And these calculations, for example, in next slides, I would show you projects where we optimize performance of equipment, district heating, biomass boiler, CHP, cooling machine, glass melting process, and etc. And we provide like optimum set points. And these set points, in fact, create value. So the value is the optimized process where energy consumption or effectiveness is increased, energy consumption is reduced. And this is a value, a real value, where we can save money. Otherwise, data collection and putting all data to the cloud is just an expenses, Our cloud solution also have GS integration with EA-PSM software desktop version, and our GS is S3 technology inside. RGIS engine, electric grid data models we have, gas pipe models, water pipe models, thermal network models. So in fact, we are capable to perform any kind of electrical calculations, compressible fluid flow, incompressible fluid flow, and thermal hydraulic flow. And coming back today to a discussion on thermal hydraulic flow, we run thermal hydraulic flow on in real time without human intervention at the server side. And this thermal hydraulic flow calculation are done through the optimization of a temperature supply or reduction, in other words, reduction of a heat losses in the heating network. I mean that consumer requires some energy and some temperature at the consumer connection to the district heating side, and thermal hydraulic calculation according to forecasted energy consumption data calculate each hour optimum temperature output from the boilers connected to the district heating company, optimum temperature output and required energy output. And all results could be later visualized on user could visualize and overview all decision on desktop version of the software. So come back to the digitalization. In general, this technology is called digital twin. I mean that it is a mathematical model of a process, and this mathematical model we run on the data which is measured from the metering device and SCADA system. And when we come to the district heating company, we create GIS model and prepare this model to the such level that is capable to calculate without human intervention. We connect to a GS model consumer smart energy meter data. If you have already data collected to some SQL database, to some cloud, we take this data from this cloud through, for example, REST API protocol. We do energy forecast and run thermal hydraulic calculation for each operation hour. But our thermal hydraulic calculation is focused on optimization of performance of a grid. And finally, you have heat production scheduling, and flow temperature optimization is, as a set point, are delivered to the control room. And here you see an example at the control room side, the environmental temperature each hour forecasted. You see here existing, and here's forecasted, and with current temperature output and optimum temperature output to the district heating network. Here you can see interesting numbers, 60 degrees. It's on the month April, at the end of April, and yes, this is correct data, and district heating company operates on such level of temperatures. When we come to the district heating company, we found that temperature output, supply temperature to the network was lowest is 70 degrees and highest probably 95. So it was like a third generation district heating company. But when we started optimize operation through calculation, through digital twin and calculation each hour, and providing set points for operation, we optimized district heating supply temperatures up to summertime average 60 degrees and 90% hours per year, probably highest, it's near to 70 degrees. Probably highest temperature was a couple of degrees more than 70 degrees. So we utilized existing infrastructure to run district heating company as a fourth generation, and in fact with only one investment to digitalization. Next, we are coming back to the heat production scheduling, and this model, how it behaves. It behaves like forecast demand and schedule boilers according to the cost penalty function. It's like a fuel price, efficiency, startup cost, and shutdown cost. And here you see that we are capable to put the nominal power, fuel type, efficiency at maximum, and efficiency curve to the boiler, and the solution. It's non-linear dynamic programming solution. Forecast the boiler output, number of boilers required to operate grid, boiler output, exact hour, minute hour range, and according to the lowest price of a current consistence of suppliers. And here you see, for example, load forecasted, it's real load, and this is capacity distributed between two boilers according to the lowest prices capable boilers operate. So couple examples about the savings in our portfolio. So installed boiler capacity is 120 megawatt for the city, and heat supply 140 gigawatt per year, and we reduced already losses near to 35%. So heat production was reduced near to 6%. It's 7 gigawatt hours per year. You can assume that we increase it, in fact, overall efficiency of a grid, calculating from energy delivered divided by primary fuel. We increase it efficiency by 5%, or just reduce it energy generation. For the city, we've installed capacity 51 megawatt and heat supply 39 gigawatt per year, 6% effect, it's 2.5 gigawatt hour per year. And for the city, installed capacity 26 megawatt and heat supply 23 gigawatt per year, its effect was on 4.5%. So in fact, it's near to 5% effect on heat production reduction due to just optimization of performance and delivering energy without any energy delivering limitation to the client. Next, at the same platform, we put digital twin of a biomass boiler. I mean digital twin, but we run burning biomass burning equations and thermal model of boiler, and run these calculations each 5 minutes. And we're capable to monitor how the fuel efficiency of a burning of a biomass fuel. And a couple examples of this digital twin solution. First example is, you can see it's just visualization on the EA-SAS cloud platform, and the issue was, from the client perspective, was that boiler steam consumption unstable. It's industrial consumer and consumption is quite unstable, and biofuel calorific quality, calorific value, and water content is unknown during burning process. When you buy biomass fuel, you know laboratory results on the calorific value and water content in biomass just after 3 days when the fuel is already burned. And we require increased lifetime or time between maintenance. So we install a digital twin biomass boiler. It's the same platform, and data collected each minute and calculated each 5 minutes. And finally, what was optimized operation, optimized great movement, fuel supply, primary air control, and finally erosion effect was limited, and set points for the operators what was provided. So it's boiler control system were operated by optimum set points from our cloud solution digital twin model. More comprehensive, this boiler, it's 20 megawatt steam output, and next example, more comprehensive, it's 30 megawatt, 5 megawatt condensing economizer, 2.5 megawatt thermal oil heat consumption, and 6 megawatt flue gas consumption consumer. And wood chip boiler, we install a data collector software as the previous project, and collected all data from SCADA control system, visualize it in dashboard, and it's the same EA-SAS cloud dashboard. And the project target was to monitor fuel consumption. So we calculate fuel consumption, biomass fuel consumption in direct methods from the burning process model, from the heat model of a process, heat consumption metering results from the temperatures and etc. So full model of biomass burning, and calculate fuel calorific value and water content in the fuel and biomass fuel consumption. All these results were compared. We store biomass fuel in the silo. Silo, it's a level of a silo, and this is from a metering, red color, and blue color from the calculated value. So silo level monitored during, for example, here it's for 4 days monitoring example, is calculated, and the metered value and biomass metering was made in direct methods. Coming back to the factory and more on digital twin capabilities of indirect measurements, we have heat exchanger and flue gas consumer, and we don't have flue gas consumer energy consumption meter installed, because flue gas coming here is 973 degrees and outcoming 260 degrees, and heat exchanger installed. But through indirect methods, when we have variable frequency drive, motor and fan makes recirculation of flue gas, but the electric variable frequency drive have measurements of energy, active energy, frequency, output measurements, and delta pressure between fan input and output. We are capable to calculate flow, mass flow, and energy consumption of a flue gas on the heat exchanger on primary side. Next, for the digital twin is, for example, glass furnace digital twin. When the glass is melting, gas is a primary energy source, and electricity electrodes as a secondary energy source. And the issue was we have quite high output temperature and don't have, in fact, oxygen meters, and burning process is controlled through air supply. Air supply is controlled by air meter, and the glass melting process air consumption is not only for the gas burning process, but also for the different color of a glass is chemical oxygen consumption due to chemical process. So it was very hard to control excess air ratio, but we installed a digital twin, and one of the output of and value for the project was that we are capable to optimize the oxygen supply to the furnace and limit the excess of air, and optimize this excess of air according to the glass and chemical reaction inside the melting process. And probably a final example on the digital twin is cooling machine, two-stage cooling machine, when we have compressors, 4 compressors, first stage condenser, receivers, and then iced water as a consumer, supplying cooling energy to consumers as iced water, and second stage 2 compressors working on the cooling machine. On the cooling camera, it's -24 degrees. So the issue is to optimize performance of a cooling machine and to maximize coefficient of performance. But to maximize coefficient of performance, what we need first, we need to evaluate what is the real coefficient of performance, and we should monitor this coefficient of performance. And with a project, we started to monitor coefficient of performance each 5 minutes. Even though we were capable to calculate in direct methods what is the consumption of a freezing camera, -24, -30 degrees cold consumption on this camera. So digital twin and calculation in direct methods each 5 minutes allowed us to understand the real coefficient of performance, and finally we optimize the temperatures of condensing and on both sides, condensing and sorry, English word, and optimizing this temperature, we increase the coefficient of performance. So when we come to the project, when we come to the company, whatever industrial or district heating company, we start from the inventory. So we collect the data, all data from the SCADA system, from the smart metering, and if you don't have some kind of meters we recommend, what kind of meters you may need to overview your performance of your grid, and do inventory what you have, all documentation, put to the GIS data, create GIS models, and all data we save on the cloud, and create a digital twin model, and identify your KPIs, what KPIs you should monitor, and what KPIs you should increase your performance, and prepare optimum operational set points, because only way is to optimize performance, and is to provide optimum how it should behave your grid, your equipment during this hour, during this minute, and you become the user. You have efficient district heating model and district heating operation, and you become the user of the cloud solution, of these set points, of this data. So our decision is divided to two parts. It's integration and living with the optimum performance of your network. So thank you for listening. Thank you for opportunity to have a presentation. And if you have questions, I would be happy to answer these questions.